Okay, so welcome to the video. And until now, we have discussed various Miller compensated op-amps, and we have seen two-stage, single stage, two-stage, and even three-stage Miller compensated nested op-amps. So in this video, we will be discussing another topology for higher gain expectations. So let's get into that. And when we say that in reality or in non-ideality, DC gain is a finite value, and it also means that the VE will never be equal to zero. It will always be some non-zero value, because at we know at steady state the DC gain is not finite, so there is something at the feedback, and VE will never be equals to zero. So now let's go back to the basic idea of negative feedback, and we have our transconductor through, and the current generated we pass through our conductances, and this is a buffer we required to isolate our amplifier from the negative feedback loop, and this is the negative feedback loop with the gain k. So we compare the desired and the actual values. So we have our desired value of gain, and we have something as our actual value, and we compare those desired and actual values, and then we derived the output based on the difference using an integrator. So basically at this point we settle down to a voltage which is basically kVi divided by 1 plus R by A naught, where R by A naught is our loop gain. It's not R by A naught, it's K by A naught. So basically like ideally it is K times Vi, but we have to take in consideration the non-ideality, which is kVi divided by 1 plus K by A naught. And when it comes back as a feedback, we have feedback voltage, which is Vi divided by 1 plus K by A naught. And thus we will always get a difference over here. So now we know at this point, ideally the voltage was kVi, but it will settle down to the non-ideality, and by pushing more current into GO1, let's say, let's consider a DC stage where capacitor is open circuit. So by pushing more current in GO1, we can make the voltage at the output larger, and basically at this point we can make the voltage larger by pushing more current into GO1 and make the error smaller. So basically we settle to a non-ideal stage of voltage at a steady state. So if we make that voltage even higher, so we can say that we can make the error due to steady state error smaller, and ideally the feedback voltage must be equal to the input voltage, and VE should be 0, but due to steady state error VE is not equals to 0. Hence the feedback loop settles to a steady state error between two inputs. And what we can do is after the loop is settled to a steady state, so after the loop is settled to a steady state, we can take these two differences. We can take the feedback and we can take the input, and like this we can again integrate, and after integrating whatever the current is produced, we can make it push forcefully through G1, which will result in increase in the voltage at this point. So what we do is we take the feedback and the input, compute the difference, and using an integrator we can somehow push current into GO1, and this is the basic idea behind the feed forward op-amp. And then we can place it in a negative feedback loop, and the addition integrator, so this is the addition integrator, and it must have a significant delay, and that delay should be we have to first let the steady state arrive for this op-amp, and then we have to make this additional integrator come into the picture. So this is a basic idea. I hope I have properly laid the idea in layman terms for the feed forward op-amp. So now let's discuss how the implementation of feed forward concept. So this op-amp is called feed forward compensated op-amp or feed forward frequency compensated op-amp. So what we do over here is we have our integrator. Let's keep things simple, and we have our buffer, and we take one integrator, we produce a current, we make the current go through uh, these conductances. As of now, let's say C2 is open circuit, all the C's are open circuit due to we are analyzing a DC voltage as of now. So we make current go through this GO2, and we have a voltage at this point. As we have a voltage at this point and we want to push a current in GO1, so again we convert the voltage into a current and we push the current in GO1, and that's how we increase the voltage as we at V0, and thus our steady state error is reduced. So this is the idea, and basically this and this element, so these all element are parallel at this node, and hence we can consider them and we can redraw them as this following circuit, in which we can replace them by the value of, like, there will be GO1, GO3 and a load uh, resistor, as well as there will be C3, C1 and the load capacitor. So together we will write it as GL and CL for everything, and we have GO2, CO2 in their places, and we have our conductances GM1, GM2 and GM3. So basically current GM1V will flow from this path, current GM2VE will flow through this path, and current GM3 times GM2VE will flow through this path. So now our DC gain, so at DC all capacitors are open circuit, so it's very simple. The DC gain will be basically voltage from this path and voltage from this path, so it is nothing but GM1 by GL from this path, and from this path it is GM2 GM3 divided by GO2 GL times VE. So this VE will go down and give us a DC gain, which is this term. So now at AC, what happens? So at AC, at this point, we have GM2V, the current, times GO2 plus this term due to capacitor will occur at AC. Similarly, this term over here will occur due to AC, and we can analyze our transfer function accordingly by seeing at the circuit, and this is what we will get um, as our transfer function. And when we resolve it and try to write it in our analog template, so this is our DC gain multiplied by 1 plus S times S by P1 divided by 1 plus S by, sorry, S over in the numerator we have 1 plus S by Z1, and the denominator we have as 1 plus S by pole, 1 plus S by pole, and from this we can say that we have a 0 at this point, and we have our first pole at GL by CL, and we have our second pole at GO2 by CO2, and all our poles and zeros are in negative, or let's say left half plane of our S map. So now we have our transfer function, which is this, and let's consider them as two different functions and plot it, and plot a Bode plot for our feed forward op-amp. So our first function is nothing but a first order function. After a pole arrives at this point, it gives a minus 20 dB per decade roll off, and our second function has two poles, so it will start with its ideal DC gain, then after first pole we have this roll off, and after second pole we have minus 40 dB per decade roll off. So these are the values for our two poles, and this is the value where our first zero might occur, and how we will see in short. So basically, when we plot for sub function f1 and f2, and we know that it is a multiplication of sorry, it is a addition, it's not multiplication, it's addition over here. So we know that it is the addition of f1 and f2, and both are the logarithmic function. So in such kind of cases, our main graph is nothing but when we add these two functions which are logarithmic, we always consider the higher value at that point. So this is how our graph or our curve will look like. So basically, when we say that we have our P1 at this point, P2 at this point, and this is where we can see that from minus 40 dB per decade, the curve is shifting to minus 20 dB per decade. So this is where we can say roughly R0 will lie, and this is where our GM1 by CL, which is our omega u loop, will lie. And we can see over here that we have plotted two curves and then taken the sum of it, and this is our complete transfer function. And we are over here, we are considering the unity gain feedback, where omega loop is basically omega u, where k is equals to 1. So now, originally, we had both the curves in logarithmic, and in logarithmic curve, we usually follow the curve with higher value. So we have this curve, and its phase will be like at P1, it will give minus 90 degrees phase shift. Again at P2, it will again give minus 90 degree, and it will asymptotically approach minus pi, but it will not be exactly minus pi. And due to the zero at this point, it will again lift up, and it will lift up to minus pi by 2. And at the point of omega u, we have a phase margin, which is basically this value, and I think it's a pretty good amount of phase margin. And we will discuss about it later. So we said earlier that we will have finite, or let's say, let's take it this way, that earlier, when we were deriving equations for Miller compensated op amps, so we said that we will have our first pole at very low frequency, and the other pole, or other n number of poles or zeros, should happen after omega loop. So, but here we have P2 and Z1 before omega loop. So for this, we need to go back to our Nyquist criterion. And basically, as we have two functions, the curve, as I told earlier, will not be exactly minus 180 degrees. So from this fact, we can comment something on the Nyquist curve as well. Let's talk about it. So let's consider a Nyquist criterion, and let's discuss it by considering like intuitively. So let's say the curve is as following, where it starts with a value, and it approaches the origin as our phase goes down, and it starts approaching the origin. And from here, as due to the effect of zero, our phase again goes up. So it again goes in this manner, and it approaches to zero. So basically, this is how our curve will look like, but it will not exceed the 180 degrees, because it will never be minus pi. It will be lesser value than minus pi. So we can draw our Nyquist plot like that, and this is our critical point. And we can say that we have enough phase margin, and the curve does not encircle the critical point, and thus the system is stable. Now, let's take a condition where we have a Nyquist curve like this, and it goes from here like this, and but like in this case we have very risky phase margin, and hence we can expect a lot of ringing in this case. So let's see. I think we are seeing some kind of conditional stability in this topology. So let's talk about stability for our system. And we have two poles and one zero before omega loop. And if pole 2 is coming before omega loop, then we need a 0 before omega loop to get away from minus 180 degrees, which we saw in our phase plot. So let's consider the following plot. And in this plot, we have omega loop over here, and we can definitely see that at the point of omega loop there is no phase margin, or even if there is, so it's very little, and these curves are not accurate. These curves are vaguely drawn just to understand the concept intuitively. And this kind of plot will give a Nyquist curve to enter the unit circle very close to minus 1 comma 0, and thus we might compromise the stability. And what we actually want is basically this thing. So what we want is, if the 0 occurs after omega loop, then we are compromising stability. So what we actually want is our 0 to occur before omega loop if there is a extra pole. So in this case, what happens is the 0 lifts the phase to minus pi by 2 again, and then we get a good amount of phase margin. So from this, we can state that the number of poles and zeros before omega loop should be such that number of poles minus number of zeros should be equal to 1 in order to achieve stability. And for this case, the curve in a Bode plot behaves like first order curve around the omega loop. So basically what we are saying is, let's say we have n equals to 2, number of poles are 2, and number of zeros are 1. So 2 minus 1 is 1. So it satisfies this condition. And when this condition is true, near to omega loop, the curve behaves as a first order. So this is what it meant. Okay, so I think we have commented enough on feed forward compensated op-amp, and let's carry on the further discussions in another video. So I think that's all for this video. Thank you for watching.